Hi Lucio, so another little video for you on continuity corrections, or anybody else who's interested, obviously. Continuity corrections are an interesting part of maths, I think. Not, don't get me wrong, not fascinating, but the reason why it interests me is because it's not that difficult to do, actually, to do the continuity correction correctly. It's not, by any means impossible to do. Um, and yet, it is something where students routinely make mistakes. So I'm very happy to talk about it because, let's see if we can eliminate those little errors. And it does massively help if you completely understand it. So, okay, we're talking about continuity correction when we use the normal to approximate a binomial distribution. And let's start with, a few facts. Okay, I like gambling on roulette. I'm a compulsive gambler. It's lost me loads of money in the past, so I need to, need to rectify that problem by looking at the maths behind it, really. Now, I only ever bet on even numbers. I've never really felt like too much of an affinity with the odd numbers, so I'm an even number better. And let's just pretend on a roulette wheel that there's only numbers 1 to 36. Now, actually, there is a zero number on the roulette wheel, and that is not considered by the casino anyway as either odd nor even. And so that's actually how they get the house edge. It's how they win, how they, are a little bit ahead of the game, if you like. It's where they get their advantage. Yeah. So if I'm only so we're changing the roulette wheel slightly from a casino roulette wheel to where it would be completely fair. Yeah. But anyway, let's say I'm only betting on even numbers and I double my money if I win. And I'm going to bet even on 20 separate spins on a roulette wheel with the numbers 1 to 36. Clearly, this would be a binomial problem. Yeah. And the number of spins is 20 and the probability of success is a half. Yeah. Now, as you well know, we can approximate the binomial distribution with the normal distribution when, two conditions really are met, or two crucial things need to be met. Firstly, p needs to be as close to a half as possible. Well, clearly this is pretty close to a half. It is a half. And secondly, the number of trials needs to be large. Now, you might argue that 20 isn't that large, and that's certainly true, but it's going to work nicely for me to show you how the continuity correction works, and it will certainly work the same way for larger numbers of n. So the way I like to demonstrate this, or the way I like to show this, is I would say that this approximates to, so I just write approx to another distribution, which I'm going to call y, which is going to be normally distributed. And I'm sure you realize that if you're going from the binomial distribution to the normal distribution, well, we need to include the mean and the variance here and here. Now, the mean you're going to get simply because the mean is the expectation. Yeah, expectation and mean are exactly the same things really in statistics, or very, very, very similar related concepts. And if you were wondering how many even numbers you would expect to hit out of 20, well, you'd expect to hit 10 evens and 10 odds, a rough guess. And you get that by doing NP, or 20 times a half, which is 10. So on average, if you like, you get 10 evens and 10 odds. So that's NP. And then for the variance, you need to do N times P times 1 minus P, which is actually going to be 20 times a half times a half, which is going to give you 5 in here. Yeah. And so that's the normal distribution we'd actually be using. Yeah. Now, let me actually show you on a, where is it? On a little animation I've got here, what that would look like. Okay, so here is the binomial distribution with 20 successes. I wonder why the probabilities aren't showing up. It's slightly off on my board. I might even exit out of it. Can you see the probabilities down there? 0.02, 0.04. This is the probability of getting 10 evens and likewise 10 odds. It's just shy of 0.18. It looks like about 0.175 or something like that there. And this is the probability of getting 9 evens and 11 odds, and 8 evens and 12 odds. So we've got a nice little probability graph showing the whole binomial distribution there. It's got, if you like, it's like a table of values, or it's the bar graph, or the frequency, or the probability graph, basically, for the table of values of the probabilities. Everything from the probability of getting 0 evens and 20 odds, extremely unlikely there, all the way up to getting 20 odds, and 20 evens and no odds. So yeah, we've got every single possible outcome there after the 20 spins have been done. Now, let me overlay the normal curve there. Now, this is the normal curve with these parameters, with the parameter mean is 10 and standard deviation is root 5. How do they get that curve? Well, I showed you this just the other day. It is a very horrible looking function, which is actually a normal distribution function. And all we've done there is plug in mu is 10 and sigma is 5. And by all means, use GeoGebra and type that horrible looking function in, and you will get exactly that curve going through there. Now, how does the approximation work? Well, it's just saying, the approximation is just saying, okay, the continuous case, the normal distribution case there, is extremely similar in shape to the discrete case. And as you can see, it genuinely is. Well, let's say that I didn't want to lose. If I'm betting on even every time, I wanted to work out the probability I get fewer than, well, 7 or fewer. Yeah, so let's write it here. If I get 7 or fewer even spins, I'll lose so much money that I won't be able to pay my mortgage. I'll lose more money than I can afford. I'll just put it like that. And I want to work out what the chances are of this happening. Yeah? So I want to work out the probability that x is less than or equal to 7. Now, naturally, I could actually, because of technology and calculators and everything nowadays, I could work out exactly what that's going to be. It wouldn't be difficult to work out exactly what that's going to be. It would be pretty straightforward too. But I want to show you with the approximation. Now, the way I normally notate it in my solution is I write probability that x is less than or equal to 7 roughly equals the probability that y is less than or equal to, and here's where I have to do my continuity correction. Now, I have to use here 7.5, and you're wondering why it's 0.5. Well, just look at the graph here, yeah? If we did the probability that x was less than or equal to 7, we'd be only using half of that bar. We would only be using half of that bar, but we need to use the full bar, and that's why we go up to 7.5. Now, if you look, this little white space should be accounted for with this little blue space here, yeah? And so it actually leads to a pretty good approximation. The approximation gets better and better and better the larger n becomes. But yeah, it's not a bad approximation. It genuinely isn't. And we'll write down both values in 1 second. Anyway, that gives me 0. Now, for the actual binomial one, it gives me 0.1316 according to this. I'm sure if I asked my calculator, it would tell me the same answer. So the actual one is actually 0.1316. But if I use 7.5, and I'm going to do this one on my calculator, so I'm just going to go to stats, normal CD. The lower I'll have is like minus a million. That's quite a low number. The upper 7.5. The standard deviation was root 5, and the mean was 10. Okay, I'm getting 0.131776. So that's not a bad approximation, it really isn't. But I hope you can see it's because of the diagram. Think about the way the normal distribution actually goes through those pieces. And it's essentially because on the way up, can you see it's basically cutting through right on the middle of the bar? Yeah. And if you put those bars together like they should be on a histogram, that's why you're going to get the 0.5. It's the most accurate way of doing it. It's only on this bar here where it doesn't really, well, it's still close to the 0.5. Look, it's going through the corners there. But yeah, you can mess around. By the way, where did I get this binomial distribution image generator? I just Googled it. Somebody else has done the hard work on GeoGebra and, basically programmed it so that it will actually overlay the normal curve on the binomial distribution. And you'll see each time why we use that 0.5 continuity correction. Okay, I hope that made sense, Rocio. Please do ask any more questions though. If you've still got a few more things you'd like to ask me, feel free. Anyway, best of luck and keep up the hard work. Bye bye.